Good morning. Um, this is the spreadsheet that I sent to you before, but I deleted some values so that I could recalculate them in front of you. And it's very similar to what the qPCR machine would give you. I deleted some extra data. It gives you like melting temperatures and such, which can be good information, but this is the essential information we need. We need the sample names, which I typed into the machine, and the target name is what the primers are targeting, which I also typed into the machine. And then these threshold values, these cycle thresholds, are what the machine output, and these are what we're going to be processing today. Now, like we talked about before, the cycle threshold value is somewhat of an arbitrary value. It's the value where the fluorescence being measured past a threshold, and or the cycle number at which this fluorescence value passed this threshold. And so, if there was if the machine gives you a cycle threshold value of 25, then that sample had more initial DUX transcripts in this case than a cycle value yield of 27. So we're going to transform these values because it was an exponential equation and inverse them because the bigger the number means the lower number of transcripts. And how we do that is first we're going to just type in equals to let the cell know that this is going to be an equation. 2 to the power of, and that's the caret symbol, negative, and then we're going to select the cycle threshold value to the left of the cell, and it should give you this very small number. This is a annoyingly long number for me, so I'm going to change the format to scientific so it's more manageable, but you can leave that there, it doesn't make a difference. Now we want the we want this transformed value for all of these, and now I can do that really easily. It's just by dragging this highlighted box down, and I'll go down to the end of the DUX4 values, and it will just copy that equation, not necessarily the number that was in that box. And to double check that it's doing it right, you can click on a random cell and click up here in the equations bar, and you note that it's referencing, see this C7 is blue, and here the cell C7 is the one that it's referencing, which is the correct one. So these are all calculating the values we want them to be. Now we need to take the averages. So each of these samples are ran in triplicate. So these polyadenylation plus values, here we're going to take the average of them. And I like median for this assay because if the machine reads one crazy outlier, then the mean would include that and throw the average off, but the median would just take the middle value. So I think it gives cleaner results, but they're both totally acceptable. So if you start typing median, then Excel will suggest this formula, which is the one we want. And we can select these 3 cells, take the median of. Likewise with the standard deviation, we want standard deviation so we can put error bars on our graph. So if we just type an equal sign to tell it that we're going to do an equation, you can start typing standard deviation and it will pop up, and we want that of these 3 cells as well. So everything was ran in triplicate, and we have these equations here, so we can just copy them, skip 2 cells, and paste them. And now these cells are taking the average and standard deviation of these 3 triplicates, which is the poly A negative fraction. And we can continue doing that, so we don't have to type equations every time, all the way down to the end of the DUX4 transcript. So now we've processed all these numbers, and these are all of the calculations you need to do just to do a basic evaluation of your qPCR data. Unfortunately, this format isn't really conducive to making graphs in Excel. So this other box over here, I typed this before, and you can retype it or you can just copy the one that I made. But I'm just going to reorder these numbers in this box. And I'm going to do that by clicking equals again, but instead of typing an equation, I'm just going to say I want you to equal this value in this box. And you have to go down the row and tell it where all of your medians are. And I'm just going to do it for the illegal DT values now for an example. But now these have moved these values just over here so that we can use them for a graph. Now, since these standard deviation boxes or calculations are directly to the right of these boxes that we've already referenced, we can, again, just drag these equations over, and now it'll be referencing the boxes to the right of those. So you can see that it's pulling from cell F2, which is the standard deviation of the poly A positive fraction. That's the one we want it to, and we can double check another one too and just see, like, look, the whole cell DNA standard deviation, yes, it's correct. So when copying so many things in Excel, I like to double check that they're referencing the right cells a lot for peace of mind. But now that we have moved these to here, we can just select the labels and the median, not the standard deviation for now. We want to create the initial graph just with the medians, and click the Insert tab up above, and for recommended charts, we're just going to insert a standard bar graph. Cool. Pretty easy. We can change the title of that before we forget what gene we're working on to ducks, and you were totally right about the nomenclature. Thank you for pointing that out. It should be italicized and only the first letter capitalized. I was using human nomenclature, so thank you. Now for adding error bars, I'm going to put this graph right here for now so we can see it while this tab pops out. But if you click on these bars, and then up in chart design, there is a button on the far left that says add chart element, and we want to add error bars, and we want more error bar options because we want to tell it what values to pull. When you click on that, Excel will generate random error bars. I don't know where it gets those values from, and I think that that's dangerous. But we want to click custom here and then specify value. And the values are our standard deviation values right here. And we want to use that as both the positive and the negative error bar. And it gives us a graph looking like this. Error bars and all. So if I wanted to do exactly this same thing for mCherry, which is the next gene on this spreadsheet, I could just copy everything we did, including that whole graph. Whoa, it zoomed really far. I could copy that, and I could paste it at the top of mCherry, and it would, oh, good to know. The graph is referencing the wrong numbers, so don't do that with the graph. But the numbers should have transferred over appropriately. Grabbing 3, oh, I had a frame shift there. We will undo this. Okay, that's what's dangerous about copying things. But it's because I copied these labels here. So let's just copy this again. Watch me fail. Just the numbers. Put it at the top of the mCherry gene. Paste. Okay, cool. And we have this whole same setup, and we can double check that we're referencing the right values. That this chart is pulling the right values. Yes, whole cell DNA. And you could just copy and paste your way through this. But I don't recommend that for learning. I am going to leave these top equations, but if you could try to calculate through it, I think it would help you better understand a little bit of what you're doing here. And then when we get your data tomorrow, then maybe you could process it yourself. And that's not a requirement. I could totally help you process it later too, but I just thought it would be cool if you could bring your data from beginning to end and then present graphs. But yeah, so fight with this a little bit. See if you get a better understanding. If you don't get all the graphs beautiful, that's fine. But I think it would be good for you to just at least look at how we process data. Okay, cool. See you in a bit.